Okie dokie. So if you have yet to pick up on one of the underlying topics of this chapter, well, I'm about to refresh your memory. That is energies, or energy, if you will. Okay? Everything seems to be revolving around the energy when we are talking about quantum mechanics and especially certain behaviors of atoms. And so that also, the idea of energy, plays along with orbitals. Okay? Now, when we start having electrons come into the mix and orbitals come into play, we're going to have some things happen, some adjustments taking place. But if we just have a one electron hydrogen atom, okay, where the entire atom only has that single electron, you notice how these orbitals are lined up. All, the single one orbital is just by itself, but then you get into the second energy level, n equals 2, and you see the s and the p are actually on the same level. See how they're even? You get to the 3, and the s, p, and the d are even. Okay? Basically, this is the only moment that this occurs. Okay? And when we have this hydrogen atom that has these types of orbitals, we call that degenerate. Not a very kind word. Okay? Typically, we don't use that word to say anything nice. But when orbitals are degenerate, that means they are just the orbitals on the same energy level are going to have the same energy. Okay? But now what happens when we start going further and further into the periodic table? So as we leave hydrogen, I call hydrogen the home base. Also, while I'm trying to figure this out, you want to get your periodic table out. Aha! Oops. So over the next, while you're getting those out, just listen up. Over the next few sections, you're going to often hear me refer to hydrogen as kind of like home base. Okay? Kind of like the majority of the time to be our starting point. Now again, for the hydrogen, we've got degenerate orbitals. But as we move over to helium, and then back down to lithium, beryllium, and so on and so forth, we are adding electrons, right? And what happens when we start adding electrons? When we start gathering electrons together, do they like to be attracted to each other? Do electrons like to be attracted? Why not? No, they don't. Why don't they? Yeah, they're negative. And what we know about like charges, they repel. Okay? So, as the number of electrons increase, so does that repulsion between them. So, in what we call many electron atoms, orbitals on the same energy level are no longer degenerate. Look how they stagger now. Look how they stagger. Now I want to go up this energy chart here. Obviously, 1s is going to be the lowest. And s is typically for every energy level, s is typically the lowest energy orbital, followed by p, then d, then f. So as we go up here, then we get to the second energy level. We see 2s has less energy than 2p. Third energy level, 3s is less than 3p. But then we get into the fourth energy level. There is something in my math that's bothering me. Then we get here. Okay? What in this fourth energy level, n, as I mentioned in the notes a while ago, n is really relative to the rows on the right hand. When we get here on the fourth energy level, what do we now encounter? This group called transitionals. And then something happens when we get into the transition metals. Look what happens. We go from 4s to 3d. And then back to 4p. We're going to address why that happens later on. But that is something that we are need to kind of store in the back of your brain. And I actually saw a funny picture the other day. It was a meme, and I guess I'm not even going to go into it, but I'll try to find it again. It was funnier as the pictures explained it than for me to try to have you visualize it. But it all goes back to putting stuff in the back of your brain. Now, this idea of many electron atoms and causing greater repulsion, which causes the orbitals to no longer be degenerate, kind of led to the idea of that fourth quantum number. And that is the spin quantum number, m sub s. If you recall, when I was doing that kind of address breakdown where I was saying that the N is like living in the United States, you remember that? Well, we got all the way down to the address, okay? 123 My Street. That would be like this fourth quantum number, okay? In the 1920s, it was discovered that two electrons in the same orbital do not have the exact same energy. So the quote-unquote spin of an electron describes its magnetic field, which therefore affects its energy. And so this fourth quantum number, the spin quantum number, gives us two values, positive 1/2 and negative 1/2. And all those values do are indicate which way they spin. Okay? And which way they spin affects their magnetic properties. So, now that we know that this fourth quantum number exists, we develop some more rules and guidelines. We get the Pauli exclusion principle. This is a very important one that we are going to abide by when we are doing the next couple of sections. Pauli exclusion principle states that no two electrons in the same atom can have exactly the same energy. Just like no one in here can have the exact same home address as your neighbor. Okay? Each has a unique location. And because of this statement here, no two electrons in the same atom are going to have identical sets of quantum numbers. Okay? Now, I'm going to let you digest this information just a little bit. Okay? Now, as we just saw, we discovered that electrons have spin. But not only do electrons have spin, but so do other particles. Okay? And call that nuclear spin. And the discovery of this paved the way for an incredible medical technological discovery. That is the MRI. What does MRI stand for? Anybody know? Magnetic resonance image. So right there in the word for MRI, magnetic, what do you think it utilizes? Maybe magnets, maybe? But in what way? So I thought it was fascinating. The more you learn about magnetic resonance imaging, how it works. And so like I said, we're going to let you digest this information just a little bit, okay? And we are going to watch a brief discussion of how MRIs work. Because honestly, the way this individual in the video describes it, yeah, you'll understand why I'd rather have him just explain what's going on than myself. It sounds like this guy has a lot of free time on his hands, or he just enjoys some, highly intelligent stuff.
So hi, my name's Daniel Vulty, and I work for the Functional Magnetic Resonance Imaging of the Brain Centre at the University of Oxford. I'm a physicist by training, but I've ended up working straddling multiple disciplines between medicine and physiology and physics and mathematics. What I'm going to try and explain to you today is a little bit about how MRI works, and more specifically about what we do here in Oxford in particular. The way that an MRI scanner works is totally different to the way that an X-ray machine works. The human body is full of water, and a water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen. Hydrogen, being the simplest element in the periodic table, consists of just a single proton for its nucleus and is orbited by a single electron. And if we consider that this is an example of a single proton, as well as having a certain volume and a certain mass and a positive charge, it also has what we call a magnetic moment, which means it's a little bit like a bar magnet, or the Earth, in that it's got a north pole and a south pole. It's also similar to the Earth in that it has what we call spin, which means it's spinning around. And so I'll represent the North Pole by attaching this screw. And just like the Earth, it spins around its magnetic pole. Now, normally it's just sitting there happily spinning. But if you place it in a magnetic field, what it's going to do is it's going to start what we call precessing, which means that there's going to be this sort of like rotating top motion of that magnetic pole. And it's not just going to precess at any rate, it's going to precess at a very specific rate that is dependent by the field strength of the magnet. The magnet that we have behind me is a 3 Tesla scanner. A Tesla is the unit of magnetic field strength. So if you can imagine that one magnet will pick up 1 kilogram and another magnet will pick up 2 kilograms, then that magnet is twice as strong. This magnet is about twice as strong as a normal clinical scanner, which has about 1.5 Tesla as its field strength. So when this water proton is placed in the magnetic field, and it starts to precess, and it's doing it at this particular frequency, this could tell us some information about the water or the environment that the water is in. But the problem is that we can't see this tiny magnetic field because it's being swamped by the huge magnetic field that we're creating with a scanner. It's kind of like trying to see a candle in front of a spotlight. The small light is just completely overwhelmed by the large light. But what we can do is, by applying a second magnetic field, which is perpendicular to the main field, the proton is going to want to try and precess around that as well. But if we apply a very small field, it's going to precess quite slowly. And so we apply the field for a short period of time, and it will tip over a little bit. And if we then turn the field off just as it gets to that point, this proton is now going to continue to spin around the large field. And now with the large field vertical, and this in a different plane, we can put a detector out to the side and we can see this rotating magnetic field. And it's going to be rotating at that very special frequency. And so that is now giving us an amount of information about how many protons have been affected in this magnetic field. And so that gives us a signal, but we really need some information about the tissue that we're looking at in the human body. And fortunately, the rate at which we go from this state, which is actually quite a high energy state, and the proton doesn't like being there, and any jostling or any effects on it, we're actually going to allow it to tip back to its low energy state where it would prefer to be. And so we get information about the thermodynamics of the system, how much energy is in the system, how much heat, how many other water molecules or other molecules there might be in the system. And so with that, we can get a contrast. We can tell the difference between different tissue types. We can tell the difference between muscle and fat. We can tell the difference between kidney and liver, or even within the brain, we can tell the difference between grey matter and white matter. Grey matter is a lot more energetic. There's a lot more going on. There's more blood flow. It's effectively hotter. And so that knocks the signal down much faster. And so when we look at an image, we get this grayscale black and white image where areas that are darker have got a lot more thermodynamic activity going on. And so we get that contrast between the different tissue types. What we do specifically here is we're looking at functional brain imaging. So we're not just trying to take a picture of the brain, but we're trying to watch the brain in action as it's working. And fortunately, when you use an area of your brain, it increases the blood flow to that area. And blood is carrying oxygen on molecules of hemoglobin, and hemoglobin has iron in it. That's the reason why blood's red. It's just like rust. And the magnetic properties of hemoglobin change when they've got oxygen attached to it or not. And so when you change the amount of blood flow to a region, you're changing the amount of iron that's flowing through that region. And so you're changing the magnetic and thermodynamic properties of the area. And so if we look at a person's brain while they're just lying there not doing anything, And then we look at a person's brain when we're flashing lights in their eyes, or getting them to perform some sort of manual task with their hands, or do calculus, or anything that requires a specific task for your brain to perform. You'll change the blood flow to that area of the brain, and we can see the difference magnetically between the resting state and the active state in the brain.
So, if you've ever had an MRI, and I'm not going to ask you if you've had one, but if you've ever had an MRI done, that's what's happening. Those magnets are essentially causing your protons in your in the molecules within your body to move in various ways that they're not wanting to, and then they can manipulate them kind of as they see fit. So, I mean, again, just listening to him talk, he's a physicist by trade, but because of his work, he's had to dabble in medicine and physiology and math and what's the other one? Physics, I think he said. But or calculus, I forget which one. But you almost take things like MRIs for granted. You think that you just go in there and have the procedure done and that's it. But just to think about the individuals who had to discover that they could do this, or at least hypothesize they could do this, go out and do it, design everything that never existed before, and then have it work and be a huge benefit to humankind. It's just that kind of stuff just always just, I don't know, kind of boggles your mind, but also kind of gets you pumped up because humans did that, as far as we know. Never know. Anyway, so that is where we come to electron configurations. Okay. By show of hands, does anybody recall doing this either in intro or regular chem? Let me put a couple of examples out there. So just like if I was thinking like 1s2, 2s2, 2p6, 3s2, 3p6, any of that ring a bell? No? Okay. That's usually about what I get. It's 50-50. And yes, at some point you did do it, but it's okay. We're going to do it anyway. So, what electron configurations do and show us are essentially the distribution of electrons in individual atoms of elements. Okay? So, the whole part about figuring out quantum numbers leads us to electron configurations and also orbital diagrams is what we're going to see also today. Leads us to that, excuse me, because that allows us to determine, as I said, the distribution, the orientation of electrons in atoms, okay? And in order for us to really understand an atom, we want to know where their electrons are. And so there are really three components to electron configurations. The first one is a number denoting the energy level. Okay, so again, that's your N. Okay, your principal quantum number, your N. And really, for the majority of the time, N is really just, like as I said, the row on the periodic table. The second component is the type of orbital. Now, a little bit ago, back when we were first looking at orbital types, S, P, D, and F, there was a periodic table within your notes that showed those sections of orbitals. Okay, and we'll do that again. And with the periodic table, that you are allowed to write on. Okay. What we might do here in a little bit. So we might actually spend more time than I thought today, which is fine. I mean, make adjustments on the fly. With the periodic table that you can write on, we will. I would say it would be beneficial if we color coded it. Okay. So we'll do that here in a moment. And the third part is a superscript. Okay. This superscript denotes the number of electrons in those particular orbitals. Now there are two types of electron configurations. There's what I call the long version, and then there's the short version, or kind of hybrid version. So you're going to learn both ways. Okay, but the further you get down into the periodic table, the more useful and friendly the short version becomes. Okay. Now, before we get into orbital diagrams, I want you to get out your periodic table. If you don't have a periodic table that says, okay. I made those special. All right, I gotta see if I can't find any copies for you.
I need a copy of the one.
Oh!
I have the one you can't write on, but I don't know the one you can write.
Lucky. I'm somewhat of a hoarder when it comes to papers. So that's the one you write when you're around. You're welcome. Don't lose those, because you're going to want those for a while.
Okay.
Okay. So I'm going to backtrack a little bit. If you need any colored pencils, I got some up here. Doesn't matter what colors you use. But I'm going to go back a little bit. Ooh, not too far. But color coding is going to be very helpful when it comes to identifying the location of your element and kind of just how you should have the ending of your electron configuration. Okay. Nope, you can have whatever color you want. Whatever color you want. You want to make a key on this one. So starting with the, I'll let you get your coloring devices. Now I know why I had my plan organized the way it did. So, starting with the S block, you've got these two columns over on the left-hand side, the alkali metals, group 1, and the alkaline earth metals, group 2. But there's also somebody who is a part of the S block that is not over here. And that is our good pal helium. So make sure you get helium the same color as the S block. So it's cool now. You can start saying S block, P block, D block, F block. Sounds like a prison. Right here in the middle are your transition metals. Okay? Those belong to the D block. And again, if you didn't hear it the first time, make sure you make a key on here. And while you're doing that, how are your periodic tables looking? Are they still, I know yours is still plenty empty, and so is yours. But for those of you who still have the original ones, are they starting to fill up with information? Or is there still plenty of room? Because we are going to write all over them Chapter 7. So just let me know at some point if you're going to need a new copy, and I'll get you a new copy.
What is the QSAT?
Oh, okay. So just whatever color you have the S block, just put S block. So it just
I
says,
don't have to write like the actual anything.
nope, you can just put, if you use green for this, just put the little color green, then put S block. Then over here, that is made up of a majority of non-metals. I'd say about 50-50, is the P block. And then lastly, you have the lanthanide and actinide series. Those are your F block. And I always get questions about when we start doing electron configurations, orbital diagrams, and when we encounter those that are, you have to travel through the F block. Okay, I always get questions regarding that, and I'll explain to you why when we get there. Okay. But as we do orbital diagrams and electron configurations, I kind of compare it to a couple things. First off, when we're doing our kind of our initial setup and progressing through it, I always relate it to a trip. Okay. And as you enter or exit a block, that is a destination. And my other comparison is, have any of you ever used or seen a typewriter? Yeah? So what happens when you get to an end of a line on a typewriter? What do you do? Yeah, you go to the next line, but back to the beginning. And that's what we have to do. We're going to be using or looking at the periodic table very much like it's a typewriter when we are doing electron configurations or orbital diagrams. Most of the time, we're going to start our home base, hydrogen, and we're just going to take a trip down the old typewriter. And tell you what, we'll go ahead and just stop it there once you're done there. So now I remember why. Okay. So I'm going to leave that up there for you if you're still coloring. I'm going to stop the recording.